Okay, the ideal gas law. The ideal gas law actually comes from the kind of collected measurements of several people, including Boyle and Charles, Martin, uh, even Avogadro. Anyway, the ideal gas law boils down to this equation: PV equals nRT. Pressure times volume equals the number of moles, that's N here, times, sorry, I can't find my cursor, there we go, the number of moles times R, which is just a constant called the ideal gas law constant. I know, very original name there, right? And T is temperature. Another way to think about this is if I take this and solve it for R, R is always equal to pressure times volume over N over T. So if I take any gas, take its pressure and its volume, multiply them, divide by how many moles of particles are in it, and divide by the temperature, what's really interesting is it always equals the same number. It's a constant. And I don't care if it's nitrogen or oxygen or a mixture like air. I don't care how big, small, temperature. I don't care, the identity. None of that matters. You take the gas and you do that ratio, it always equals the same number. It's a constant. Well, actually, that's kind of cool because that helps us to do some calculations with gases. And so PV over NT equals a constant, the ideal law, gas law constant. What does it actually equal? Well, it depends on the units. If you think about this, P could be pressure, so I could have pascals or atmospheres or bars or anything. This volume, so maybe I do milliliters or liters or cubic meters or something like that. N is moles. Now, there's only really one unit, mole, right? That's it. And temperature, we always use Kelvin. Got to use Kelvin because we need that zero with the absolute zero. We need that to be set right down at the true value of 0. So don't use Celsius, don't use Fahrenheit. Always use Kelvin for temperature. So I know I'm going to have moles and Kelvin on the bottom for the units of this R. On the top, well, it just depends what I'm using for pressure and volume. Maybe one of the most useful values is this one, 0.08206. Why? Because, all right, moles and Kelvin are on the bottom. For pressure, we've used atmospheres, and for volume, we've used liters. All right, and so when you use those units, 0.08206 is what R equals, and we very commonly measure pressure in terms of atmospheres and volume in terms of liters, and so that would be consistent with often used units of those. But again, I can use all kinds of different ones. If I take this and use kilopascals or liters, moles, and Kelvin again, it turns out to be 8.31451 or 8.314. Right? Why would I use that? Because actually a kilopascal, if I use instead of a normal pascal and I do a kiloliter, well, a kiloliter is actually the same thing as a cubic meter. That's just like a milliliter, same thing as a cubic centimeter. A cubic meter, pretty big cube, right? But a cubic meter is a kiloliter. All right, and so think about that. Here I'm using pascals, which are the MKS units, the base units, right? Meter, that's a base unit. Kelvin, that's a base. Mole, that's a base. This is when everything is in the correct MKS system of base units. That value is 8.314. And so that's a useful number as well. And when we actually go to other calculations involving energy, turns out you can do energy, and we use R there as well, and 8.314 is the unit we use there because, again, that's the base units in the MKS system for the SIs. And so those are two ones that you should be familiar with. There's plenty of other ones out there as well, but almost always we'll use one of those two. All right, so let's do an example here using PV equals nRT. Example 9.9. Let me get to it here. Actually, it's back here. Example 9.10. Ooh, I'm close. There we go. Example 9.9. Methane, CH4, is being considered for use as an alternate automotive fuel to replace gasoline. True enough. All right, 1 gallon of gasoline could be replaced by 655 grams of methane. So that's about how much we need for the same punch, I guess, the same amount of energy. 655 grams of it. Now keep in mind, this is a gas. Methane is a gas. It's natural gas. It's the gas we use in our stoves sometimes or our furnaces. Natural gas, methane. All right, so 655 grams of it. Gases don't weigh a whole lot, or I should say they're not very dense, right? And so the same volume doesn't weigh a whole lot. So they want us to calculate what is that volume at 25 degrees Celsius, which is more or less room temperature, and 745 torr, which is a little less than 1 atmosphere of pressure. Okay, let's give this a try. We've got 655 grams of this methane. Temperature is 25 degrees Celsius. Pressure is 745 torr. Remember, that's the same thing as millimeters of mercury, right? What is the volume? Okay. PV equals nRT, which means the volume is going to equal nRT divided by pressure. So if I could just know how much moles, R, temperature T, and pressure, I could plug it all in, and that would tell me what my volume is. That equals it. Well, let's see. I don't know moles, but I know grams. I know I have 655 grams of methane, CH4. I can convert that to moles, grams to moles. 1 mole of methane. Well, let's see. Let's add that up. Go on the calculator. 1 carbon, 12.011, and 4 hydrogens, 1.00794. So 16.04 is my molar mass of methane. So that would cancel out. 655 divided by 16.04 is, oops, I typed it in here instead of here. Let's go to the calculator and try that again. 655 divided by 16.04. All right, 40.84. 40.84 moles of methane. Okay. That's what my N is. N equals that. So I know what N is. T, temperature, they told me is 25 degrees Celsius. Can't leave it there. Got to go to Kelvin. So how do I convert to Kelvin? We add 273.15. So 25 plus 273.15 is 298.15. There's something that you'll probably get used to seeing quite a bit. 298 Kelvin, 290.15 Kelvin is about room temperature, 25 degrees Celsius. Pressure. They gave me it. They said it was 745 torr. 745 torr. Torr is the same thing as a millimeter of mercury. And what do I want to convert that to? Well, let's think about this. I want volume, and my units of R could be in cubic meters. Remember, if I use the 8.31451, or if I use the other value, 0.08206, my volume would come out in liters. That sounds good. I want liters, which means I want the pressure in terms of atmospheres. That's the unit I want to use. I need to use consistent. And so convert millimeters to atmospheres. All right, 1 atmosphere is 760 millimeters of mercury. I almost said torr. That wouldn't make much sense. Millimeters of mercury would cancel. Let's see what that equals. 745 divided by 760 is 0.980. So 0.9803 atmospheres. There's the pressure then that I can feed into this equation. All right, so I've got it all here. I can put it all in. N was 40.84 moles, right? R, I'm using 0.08206. That's liter atmospheres per mole per Kelvin. Temperature, 298.15. And the pressure, 0.9803 atmospheres. Put it all in. That will equal my volume. All right, back to the calculator. 40.84 times 0.08206 times 298.15 divided by 0.9803. Okay, if I did that all correctly, my volume is equal to 1,019 times 10 to the third. So 1,019 liters. Again, I know liters because I used the value for R, 0.08206, which had liters as its unit of volume. So to get the same amount as 1 gallon of gasoline, the same amount of energy, I would need to carry around 1,000 liters of methane. Well, I don't know, my tank on my gas, on a small car would be about 8 or 9 gallons, something like that. On the larger ones, you have much larger, up to maybe 20 gallons of gasoline. I mean, imagine if I had 20 gallons, so I'd have to have 20 times that, so 20,000 liters of methane gas. So, you know, the tank would probably be bigger than the car itself. But I suppose you could do it. All right. Now, the PV equals nRT is really useful because it always equals R, right? This PV over NT always equals R, no matter what the gas is, and no matter what its temperature and volume and pressure. Which means, let's say I have a sample of gas and I heat it up, heat the temperature up. What's going to happen? What's going to happen to its volume? What's going to happen to its pressure? What's going to happen to the number of moles? Well, as long as I don't open it up and add gas or let gas leak out, I guess the moles are going to stay the same, right? But what's going to happen to the other ones, right? It's changing state, and I can talk about the initial and then the final state that it turns into. Right? And in both of those states, if I said PV over NT, it's always going to equal R. So they both equal the same constant, which means PV over NT for each state equals each other. And that's what I've written here. Did I say written? I don't know. But written. All right, PV over NT in state 1, well, that equals R. Heat it up. Something else happens with the volume and pressure probably, but all right, call it state 2, so PV over NT in state 2, that also equals R, so they have to equal each other. This is kind of what's called the combined gas law. The idea that two different states, the before and after state, if you say PV over NT, they're going to always equal each other. And I know what it equals R as well. What's nice is I don't even have to worry about the values of the units in R, because as long as I use consistent units, you know, if I want to use millibars over here and millibars over here, then they'll still equal each other. Okay, because any conversion unit, I would have to do it to the same on the both left and the right, and they would just cancel anyway. You know, so if I do centimeters for volume and centimeters for volume here, we're good. Right? Moles and temperature, well, that's moles and Kelvin. We really don't have other units for those anyway. So the combined gas law, and I always use this as a jumping springboard, whatever, to go into almost any problem involving a before and after state. Okay, and we're going to do an example here in just a second. If I limit what's allowed to change, so for example, let's say I keep this in a water bath, the temperature of my gas sample is constant. So I take it and take whatever the sample is and again submerge it in some kind of a flexible container, whatever, down in a water bath, so it's always 25 degrees Celsius, right? Whatever else is happening to this gas, it's going to maintain that same temperature, for example. Then if you look at, and for that, let's say that I don't allow anything else to go in and out. So it's a balloon, it's sealed, you know, I'm not letting gas escape, or I'm not blowing any more gas into it. So then in my combined gas law, N1 is the same thing as N2. Maybe they're both 5. Got a 5 on the left, a 5 on the right, so they just cancel out. They're the same. You can cancel them, cross them off. The temperature, again, I'm saying, hey, in my experiment here, I'm not letting that change. So T1 equals T2, that cancels out. So what does that boil down to? This is what I'm doing here. I'm canceling those out. It boils down to just P1 V1 equals P2 V2. That condition, where the only thing you're allowed to change is pressure and volume, because everything else is being held constant. Right? Pressure and volume 1 equals pressure and volume 2. Those conditions are called Boyle's law. Boyle's law. And if you think about this, the idea that pressure times volume is going to be some constant then means that if pressure increases, volume is going to have to decrease in order for me to get them to always equal that same constant. Right? I mean, for example, let's say pressure was 4 and volume was 5, whatever. So that multiplies together to give me 20. Right? If I let the pressure go up, so let's let let's go let the volume go up instead, just to make these numbers easier. If I let the volume go up to 10, but they still have to multiply together to give me 20, then I guess the pressure must have gone down to 2. And I keep playing this game. If I let, again, let's let the pressure go up to 20 this time, then I guess the pressure has gone down to 1. Right? As one goes up, the other one goes down. That way, when you multiply together, you still get that same constant. Right? They're inversely related to each other. Right? Pressure goes up, volume goes down. That's Boyle's law, and that's what he noticed. See, he said, wow, as I increase the pressure of a gas's volume goes down. And vice versa. Right? So P1 V1 equals P2 V2. That's Boyle. pretty easy equation to use, because if I know the initial pressure and the initial volume, then I say, hey, I increase the pressure to some P2. What's the new volume? Plug in the numbers that you know and solve for what you don't. In that case, solve for V2, and you've got your answer. What if the only things I allow to change are pressure and temperature? So this would be like the case of, like, I take my gas sample, I put it in an enclosed steel box that doesn't expand or contract. It's just locked in. That volume is the same, doesn't change, right? But I allow temperature to change and I allow pressure to change. So then, in other words, I take that steel box, I put a flame underneath it, I increase the temperature. What's going to happen? Since the volume can't change, the only thing that can is pressure, and so it's going to go up, it's going to go down, it's going to change. In this case, it's actually going to go up. That is called a Montan's law. Montan's law, Montan here, is where only pressure and temperature are changing. Volume and N, the number of moles, are being held constant. Well, if I do the same thing here and take the ideal gas law, and you think about that, if my volumes are constant, so V's cancel and the number of moles is constant, I'm not adding and removing gas, so N's cancel. What am I left with? Just P over T, and that's what we got over here. P over T1 is equal to P over T2. So if those are the only two things changing, you use a Montan's law. Notice it's really just the ideal gas law combined, where you just allowed some things to be constant and so they cancel. Charles' law? Charles' law was only volume and temperature is changing. V over T equals V over T. And in both of these cases, they're going to be directly related. They're proportional to each other. So if V over T has to equal some constant, again, let's go with 20, let's say. All right, and so maybe it's 200 volume and 10 on the bottom, that equals 20. All right? If I increase the volume to, say, 400, then I'm also going to have to increase the temperature to 20 for them to still divide and give me 20 as the answer there. As volume goes up, so does the temperature. Okay. In this case, for Charles' law, it's kind of like a balloon. And if I heat that balloon up, the volume of the balloon is going to get bigger. As temperature gets hotter, the balloon expands and the volume gets bigger. Same thing with the pressure. If I don't allow that volume to change, but I just lock it into a steel box, as I increase the temperature, the pressure is going to build and also increase inside that box. Okay. All right, number 4, the last one, Avogadro's law. That's where you're only allowing volume and N to change, the number of moles. This one is, I think, the most obvious. If I take the balloon and I blow more air into it, what happens? It gets bigger. I'm only allowing volume and the number of moles to change. Pressure and temperature are the same. I'm not heating the balloon up, and I'm not changing the pressure of it. It's still 1 atmosphere of pressure on the outside, which equals the pressure on the inside, and that's why it stops getting bigger or it stops getting smaller, because the pressures are the same. Right? So volume and N are proportional. That's called Avogadro's law. Example 9.6 to show how this works. A sample of carbon dioxide, CO2, occupies 0.3 liters at 10 degrees and 750 torr. So, pause here. They gave me pressure, they gave me temperature, they gave me volume. Okay. It says then, what volume will this gas have at 30 degrees temperature and 750 torr? So, 750 torr, they gave me pressure here. The pressure hasn't changed. The temperature's gone from 10 up to 30. So they've heated this up, and they're asking me what's the new volume of it. So I'm allowing temperature and volume to change. Well, that's Charles' law, and we just talked about that. All right, but how do we actually calculate it? All right. You don't have to remember Charles' law, Boyle's law. You just have to remember the combined gas law, the idea that P1V1 over N1T1, equals P2V2 over N2T2. Right, you always take that ratio and they always equal each other. And in this case, the pressure was 750 initially and 750 finally. The state 1 and the state 2, they're the same. So my pressures are going to cancel. Put the same number in. They're identical. They haven't changed. Okay. And I always like to lay it out here. Here's my state 1 with V1, T1, T1. Here's my state 2, V2, T2, P2, right? And I write in my numbers, and if I have to convert to a unit, I do it right then and there. And that organizes it nicely. Okay. What else has not changed? They said I didn't add or remove any gas, and so N1 and N2 are the same, therefore they cancel. So again, I get down to just V1 over T1 is equal to V2 over T2, which is Charles' law. Here's all my data up here, 750 torr. Again, that canceled anyway. My volume 1 was 0.3 liters. They're asking me, what is the new volume? So volume 2, I don't know, question mark. That's what I'm solving for. My temperature was 10 centimeters. I know I can't plug in centimeters, so add 273 to that, so 283 Kelvin. My final temperature was 30, so add 273, that's 303 Kelvin. All right, so I've got the numbers that I can plug in here. Do it right here. Volume 1, 0.3 liters. Temperature 1, 283 Kelvin. Volume 2, I don't know. I'm trying to solve for that. Temperature 2, 303 Kelvin. Solve that now for V. V2 would equal, calculator, 0.3 divided by 283 times 303. All right, 0.321. 0.321. What are the units? I put liters in here, so my units are going to be liters. I put liters here. That's a 1 here. There's my new volume. I always like to step back and say, does this make sense? My initial volume was 0.300. My new volume, 0.321. It's gone up a little bit. That does make sense because I increased the temperature a little bit, right? From 10 degrees up to 30 degrees Celsius. Make it hotter, it got bigger. All right, so there's my new volume. Whatever is changing, whatever is not changing, just make your little table. Cancel the things that are identical because they just cancel out, and then whatever remains, plug in with the correct units, right? Plug them in and solve for what you need to solve for. In that case, it was V2 that I needed to solve for. So they're all going to be pretty much identical to that. STP, you'll come across that terminology. That stands for standard temperature and pressure. This is similar, but not the same, similar to the idea of a standard state. All right. Here it's just, this is for gas laws and standard temperature and pressure and agreed upon just kind of standard conditions. Temperature is going to be 0 degrees for STP. All right. 0 degrees, which is 273 Kelvin. 273.15. And so if someone just, if the homework problem says, hey, you got a gas under STP, then you know it's 0 degrees Celsius. Right? The pressure is 1 bar. That's standard pressure. So you know what the pressure is as well. They're giving you essentially temperature and pressure when they say, hey, it's under STP. All right. One note. Since 1982, the standard pressure has been defined as 1 bar. Prior to 1982, they actually defined it as 1 atmosphere. Most people just worked in units of atmospheres. And, you know, the average pressure on Earth at sea level is 1 atmosphere. And so, standard pressure of 1 atmosphere. All right, but the bar is related better to the SI units because a bar is 100,000 pascals. We talked about before, where an atmosphere is 101,325 pascals. And so they said, you know what, that's close enough. And so they switched it. They said, you know what, instead of 1 atmosphere, we're going to say it 1 bar. That happened back in 1982. Officially, that's the correct STP then. It has taken a long time for scientists to kind of switch over their mode of thinking to that. And so many chemistry textbooks, you'll still see it listed STP as 1 atmosphere. Pretty typical. And including, I believe, this textbook. All right, so STP, just check what that textbook does. All right, it might mean 1 atmosphere. It might mean 1 bar if they've correctly updated their textbooks and are using it what the new standard is. Okay. Now, under STP conditions, I know temperature, I know pressure, you could ask, what is the volume, what does V equal, if I have exactly 1 mole of gas? Because, see, the volume would equal, well, PV equals nRT, so nRT over pressure. Right? And if I put those standard numbers in for pressure and temperature and 1 for a mole, that'll tell me my molar volume under standard conditions. Standard molar volume it's called. If you go ahead and plug in those values, nRT over P, so 1 mole, 8.31451, that's the value for R in the SI units. Right? MKS SI units. 273.5 is temperature, and 1 bar, which in SI units would be 100,000 pascals, that equals 0.02271 cubic meters. Again, that's the MKS SI unit for volume, and convert that 22.7 liters. All right, so under standard conditions, you take 1 mole of any gas, it's going to equal 22.7 liters of volume. All right. And you get a sense, that's a pretty big box, but 22.7 liters. That's just kind of gives you a visual to base it on. Now notice if they use the older version of STP where instead of 1 bar it's 1 atmosphere, and you did the same thing, you plugged in, turns out to be 22.4 liters, just a hair smaller. Because again, 1 bar, 1 atmosphere are pretty close in value.